University oceanographers. Last time we discussed physical properties of water, significance of the high heat capacity of seawater, the effects of temperature and salinity changes in seawater, on the density of seawater, and where the ocean water gets its salt from. We also talked about pH of seawater, and that is the acidity of seawater, and ocean acidification problem in the global ocean system. We're going to get back to this ocean acidification problem later in the semester, but today we're going to talk about salinity and temperature changes in the oceans, both at the surface and with depth. So you're looking at here the Pacific Ocean water system, and you see the salinity changes from the equatorial regions with 37 milliliter per thousand liter in the equatorial region. That's a very high salinity, and as you go towards the north, you realize that the salinity changes and becomes lower, down to 32 milliliter per thousand liters. So the ocean waters globally have these kinds of fluctuations in salinity and density, therefore, and we're going to talk about what processes control these kinds of changes. So today, I'm going to talk to you about density structure of seawater. And first, we're going to look at surface processes. And it will be very clear that solar radiation dictates to surface processes in the oceans, and evaporation and precipitation rates and the differences between the two will really control what happens in surface water in terms of its salt content and the temperatures. And then we're going to look at the salinity changes in surface ocean waters. Then we're going to define a pycnocline, a specific term in oceanography, in physical oceanography, that you need to really learn how to spell and how to write down. And pycnocline basically is a zone of rapid salinity change in ocean waters as you go deeper below 100 meters or so. And then that will take us to the concept of overturning in ocean waters, and we'll get into that very briefly. Then we're going to look at temperature and salinity changes with depth in the ocean waters, and that will take us to two concepts, thermocline and halocline. And thermocline, as the name shows, thermo, that's related to temperature, and cline, that's basically a curve or a surface with certain inclination, and thermocline, basically a surface on which temperatures remain the same. And by the same token, halocline is basically related to salinity changes, and halo is associated with halon content, which is the salt content of seawater. And as long as you're on the same halocline, basically you are on the surface of same salinity. And we're going to look at temperature salinity diagrams. We call them TS diagrams in physical oceanography. And we're going to take a look at density-based water layers in the oceans. And once we go through the basic principles of that, I'll take you through several profiles across the Atlantic Ocean from the north to the south. And one of them is going to be the temperature profile. And we're going to discuss why and how the temperatures change in the Atlantic Ocean. And then we're going to look at the salinity profile in the Atlantic Ocean, also from north to south. And then we're going to take a look at seasonal changes and temperature profiles of polar oceans and what really happens in the polar regions to change the temperature profiles of ocean water so dramatically and on a seasonal basis. So let's take a look at now first surface processes affecting global ocean water density. And we're going to basically look at these three profiles first. And the one on the left is the temperature profile going down to 200 meters. And the temperatures are increasing from left to right in degrees Celsius. And the second profile in the middle is the salinity profile, also down to 200 meters at depth. And the salinity is basically the salt content, and it's changing from 34 to 38 per thousand. And the density given in kilogram per cubic meter, increasing from left to right. And these profiles basically represent the Central Atlantic Ocean water properties in general. So, to begin with, we should say that solar radiation and the atmospheric pressures and the atmospheric uh, weather conditions strongly control the surface water temperatures and also the what happens in terms of weather conditions. And the sea surface temperatures strongly affected by solar radiation in the sense that in equatorial regions and tropical regions you have very high rates of solar radiation, and as a result you have high rates of evaporation. But also in tropical regions you have high rates of precipitation. And so the evaporation and precipitation rates and the differences between them really control the salinity at sea surface. And so if you look at the first profile on the left in the Central Atlantic Ocean, you see that surface temperatures are pretty warm, up to 28 degrees Celsius. And because of the winds and the waves and the air-sea interactions that we're going to be talking about next time, the surface water is pretty well mixed. So you don't see significant temperature changes within the first 40 to 50 meters in the ocean water. But after that, as you go deeper into the ocean, you realize that seawater temperature is decreasing steadily, and all the way to 200 meters, basically we changed our temperatures for as much as 8 degrees Celsius by just simply going deeper. And if you go look at the salinity profile, again, at the surface, within the first top 40 meters or so, you have a very well mixed layer with not much change at all in salt content of seawater. But after that, as you go deeper, you will realize that the salinity is ever slightly decreasing. And so we started off here 37.2 per thousand, and by the time we got to 200 meters, you are well below 36 per thousand. So that's basically decrease in salinity. And if you look at the density changes, you realize that at the very surface, the density is not that high. And also we have a vertical basically curve here saying that the density doesn't change, just like the temperature and salinity profiles have shown to us with depth. But after about 40 meters or so, and particularly after we pass through the 50-meter depth in the Central Atlantic seawater, you realize that the density is now increasing quite steadily. And that's because basically the ocean water is getting much colder. And as it does, as we talked about in the last lecture, the density is increasing. Cold water is denser. So if you look at these two profiles, temperature on the left and density on the right, you're going to see that they almost show a mirror image sort of relationship with decreasing temperatures with ocean water. You see the density is increasing. So what that tells us that the temperature is a significant controlling factor when it comes to density of seawater. So let's take a look at, go deeper than a little bit, 200 meters into the ocean water system and take a look at what happens to density with depth. So with the top 100 meters, you have a very mixed surface water. So just like we saw in earlier profile, you have almost a little vertical line there indicating that the density changes are not significant at all, almost the same density down to 80 to 100 meters. And then you'll get this green line, green curve. You realize that the density is increasing, in fact, quite significantly within a very short distance with depth. And then there is this sharp bend, and then the density then keeps increasing, but not as strongly as what we saw here. So this zone down to almost 500 meters, along which the density of seawater change very significantly. That is a zone of pycnocline, a very rapid density changes within pycnocline. And below 500 meters depth, the density of seawater continues to increase, but not as rapidly as what we saw within that pycnocline zone. And by the time we get to about 2,000 meters, we see that after 2,000 meters, all the way down to the bottom of the oceans, as much as 4,000 or 5,000 meters, basically there's no density change at all. You see that vertical curve going down, vertical line, indicating that no density change. So the density is relatively homogeneous all the way to the bottom of the ocean after we pass through the 2,000 meter depth in the oceans. And the controlling factor here is basically rapidly cooling seawater temperatures as you go deeper into the ocean. And after a while, the density curve becomes stable. But there are times and places where the water density in the global ocean system may not be quite stable. When and if there is much more dense water standing on top of less dense water, this is going to create an unstable water column, and the dense water on top of the light water will then rapidly sink. And the sinking process is going to cause overturning of the water column and will bring that dense water deeper into the oceans while the lighter water basically rises to the top. This is particularly very common process in polar ocean systems with the start of the winter season, and we call this process overturning. Overturning is a very important process in the oceans because it's the beginning of the cold, deep water masses in the oceans, as we will see later on. And that overturning also brings lots of dissolved oxygen and nutrients into deeper ocean water. So overturning is a significant phenomenon in the oceans and controls to some extent the thermostat of the oceans. So now we're going to look at the temperature and salinity changes with depth in seawater. And we're looking at, on this diagram, two parameters, two controlling factors. One is the salt content, and the other one is the temperatures of seawater. So you're looking at basically here on the horizontal axis. Below you see the temperatures rising from 0 degrees on the left to over 10 degrees Celsius, and that is basically shown by this green curve, and the salinity given by 32 per thousand on the left to 34 per thousand and higher on top, and the salinity is shown here by the red curve. And what you see here is that in the very top 100 meters or so of the ocean waters, you have a well-mixed water column, and temperature changes are not significant at all. But as you go deeper below the 100 meter zone, you will see the temperatures are rapidly diminishing and seawater getting cooler and cooler. And by the time you get to 500 meters here, we ended up with basically water temperatures decreasing as much as nearly 10 degrees Celsius. So this zone of the top nearly 500 meters, that is this green zone, in which the temperatures change very rapidly with depth. We call this the zone of thermocline. And thermocline, we define it as a zone with a rapid change in seawater temperatures. And the temperatures continue to go down below this thermocline zone, but not as at the fast rate as we saw within the thermocline zone. And as you can see, by the time we get down to about 2,000 meter, just like we saw with the density profile in the ocean waters, you end up with basically having pretty stable cold ocean water all the way down to the bottom of the ocean system. So this vertical line here, profile, basically defines a isothermal water, meaning same temperature water. Okay, and the data that are shown on these profiles basically are real data from the northeastern Pacific Ocean. Now let's take a look at the salinity changes and the halocline given by this red profile. Again, in the very top part of the ocean water system, the salinity changes are very minimal. It's a well-mixed zone, and the line is a little tick mark there is nearly vertical. But right after that, after 80 to 100 meters, the salt content is increasing, and the salinity is increasing, and you see that once we get into this green and then the yellowish tan color, the salinity profile is basically increasing quite rapidly. So this zone of rapid large change in salinity with depth is called the halocline zone. And you realize that the halocline and the thermocline curves have opposite images. And so with depth, the temperatures are decreasing, but with depth, the salinity content of seawater is increasing. So just about after 2,000, 2,500 meters, the salinity of the seawater is pretty much the same. So this part of the salinity profile, we call that isohaline, iso meaning the same, and same salt, basically salinity content of seawater. So the density structure of ocean water is extremely important for ocean currents and mixing of different seawater masses with different physical properties. And because of that, oceanographers always look at the temperature and salinity properties of seawater and measure them and identify different seawater masses by the temperature and salinity profiles of ocean waters. We call these temperature salinity profiles TS diagrams. So you're looking at basically a typical TS diagram. The temperature, the T, is given by degrees Celsius along the vertical axis, increasing from 0 degrees Celsius to 20 degrees on top. And the salinity given by per thousand, increasing from 33.5 to 36.5 to the right. And You see a bunch of green lines, curves actually, on this diagram. Those are same density curves. You see the Greek letter rho, a symbol of density in oceanography and actually in all physical sciences. And you will realize that the density uh, lines, density curves basically are dipping incline, they're not straight. And you see the increase in density as you go to the lower right hand side of this diagram. So this is the high density part of ocean water, and that is the low density part of the ocean water. So these are um, um, iso density lines, and as long as you stay on this particular green curve, basically your density remains the same, about 1.0260, and in given in basically gram per cubic centimeters. So um, many combinations of temperatures and salinities can give us different density characteristics of seawater. And two different waters having the same density may have totally different salinity and temperature characteristics. So I'm going to give you an example of that. Let's take, for example, water A and then water B, and you realize that water A has a temperature of about 1 degree Celsius and the density salinity of about um, right there 34.7 or so. So, but it sits on the density curve of 1.0270 gram per cubic centimeter. Now let's take a look at another water column B. And first of all, let's say that this point B is also sitting on the exact same density curve. So A and B have exact same densities, but if you look at the properties of water column B, you will realize that it's actually much warmer than water A. Water B has temperatures of nearly 13 degrees Celsius, and it also has much more salinity in comparison to the water A. And yet they both have exact same density. So basically, water masses may have similar densities but totally different properties. And this is going to be a very important concept when we start talking about the ocean currents, particularly deep ocean currents. And so when you have this line of mixing between A and B, so any water mass or water column with changing physical properties along this line will basically have same salinity but different mixtures of A and B. Okay. We also have a term called coupling, and this is basically mixing and sinking process when two different water masses, surface ocean waters, converge and mix. And when you mix two different water masses, the resulting water mass will always be denser and will sink, and that whole process is called coupling. So we have another example here of two different waters with totally different salinity and temperature properties, as you can see, and they basically but have the same density. So let's take a look at these 2 points again. Point A has a temperature of about 0 degrees Celsius and the salinity of 34.23 per thousand. Point B has a temperature much higher, 11.4 degrees Celsius, and a salinity of 36 degrees. But you do realize that both A and B actually lie on this same density curve right here. So they have the same density anomaly. But the gradient of density anomaly or density changes is not constant. So that's why these red curves are inclined or dipping at different angles as you go from left to right. So they're not straight lines, but they're rather actually curving. And that means that the density anomaly has a different change in gradient. For example, point A with the temperature and salinity characteristics as we talked about a few minutes ago. If you increase the temperature by as much as 5 degrees Celsius, so you're going to take this water higher up by 5 degrees Celsius, you will see that the density of this water is going to be basically decreasing as you raise the temperature. At point B, keep the salinity constant, but increase the temperature by the 5 degrees Celsius. You will realize that the density of water at B will also be getting smaller, and the densities of these two water columns, which happen to be on the same density curve to begin with, will look completely different. So this is what we call the nonlinear response. If we change the physical properties of seawater, keep the temperature constant, but change the salinity, or vice versa. So I am going to ask you to find out the density anomaly of seawater with a temperature of 15 degrees Celsius and a salinity of 35 per thousand using this diagram and see what you get. Okay. So ocean waters with different densities and physical properties form different layers in the oceans. That's why the ocean waters are very much layered, and pretty light, less dense surface waters remain at the surface. So we're looking at a block diagram here, and from left to right we go from 60 degree north latitude towards 60 degrees south latitude. So this is a north-south latitude in any given ocean. And on the left-hand side we're looking at the depths in meters, sea level 0, and then 1,000 meters, and increasing down to over 4,000 meters here. The green area at the bottom of this diagram is the seabed, and so the green area is basically the seafloor and what we have in terms of ocean crust underneath. So this is the water column we're looking at, that we're interested in looking at. So we're going to look at the density changes in ocean water from the top to the bottom. So in the equatorial region, pretty much all the way to from the 0 degree to 20 north, 20 south degree north and south latitudes in this green area at the surface, we have a very light surface water. That means that the surface waters are pretty warm and the salinity is not high at all. So the density is about 1.023 gram per cubic centimeters. So warm, low salinity surface water in the equatorial regions. But as we go north, um, towards 20-degree north and south latitudes, towards higher latitudes, all the way towards 42 degrees north and 42 degrees south latitudes, um, the surface water is still warm because you're still getting high solar radiation. But here at these latitudes, evaporation rates basically pace out the temperature changes. So you have higher rates of evaporation, and that's why the salinity is higher, because the surface waters now are more salty. And as a result, you have this now blue layer with increased basically density. So we went from 1.023 to 1.0267 gram per cubic centimeter at these latitudes with higher salinity. Because the salinity is now higher than what we saw at the surface in equatorial to tropical regions, this water sinks and becomes a distinct layer, if you will, a tongue of a little bit saltier and therefore denser layer underneath the equatorial tropical ocean waters. As we go further north and south, and towards the 50 and 60 degree north and south latitudes, right here, so we're looking at the second green zone here, both cooler temperatures and relatively higher salinities at these latitudes basically create even denser seawater. And so this water now has a density of 0.0270 gram per cubic centimeter and denser than what we saw in the mid latitudes, so it will sink underneath these other two layers that we talked about earlier. Well, going further to the north and south, the subpolar ocean water is cold pretty much throughout the year, but particularly in winter times, extremely cold. So you see that the temperatures dictate to the density profile of the polar regions. So the seawater became much denser in comparison to what we saw in the mid latitudes, and therefore this extremely cold surface water, and it could be a little bit saltier as well depending on the seasons, and we'll talk about that very shortly. You end up with basically having this polar water being extremely dense and therefore sinking. At the very pole or near the pole, the surface waters are extremely cold throughout the year, with sometimes permanent ice, and therefore they sink underneath all other layers in ocean water. So almost each ocean has a very similar layered system based on the density differences controlled by salinity and temperature changes. So let's take a look at the temperature profile of the Atlantic Ocean, and we're going to be basically heading from nearly 55, 60 degree south latitude across the equatorial region and towards the North Pole over 60 degree north latitude. So imagine that we're taking a hike right along this red line across the Atlantic Ocean, all the way from the south to the left and to the north on the right hand side. And on the right hand side you see the color coding for temperatures in degrees Celsius, cold colors, starting with purple, 0, and then you go to very warm temperatures, nearly 28 degrees Celsius with orangish red. And on the left-hand side, you have the depth in terms of meters from 0 sea level to 6,000 meters. The gray area, again, is the seafloor, and it's highly exaggerated, of course, distance versus depth. So that's why we have these enormous spikes, but actually it's not as spiky as what you see here. But notice that as you go from south to north, at some point you're crossing the mid-Atlantic ridge, right there with high elevation, bathymetric elevation above the sea level. Okay, the black lines on this profile show the equal temperature. We call them isotherms, as we mentioned before. And we see the colors shown in terms of 0 and 10 degrees Celsius and 20 degrees Celsius as you go closer to the surface. Here's the 10 degree, here's the 20 degrees Celsius isotherms, these black lines. In the upper 1,000 meters in the Atlantic Ocean, temperature changes are very rapid. As you see here, the isotherms are clustered together, compressed together, because that means that with little depth, the temperature is changing very rapidly. But as you go deeper, you realize that the distance between the isotherms is opening up and much wider. That means that with depth, temperature changes in the Atlantic Ocean really not significant. So you have to go a long distance in terms of depth between each isotherm to change your temperatures. So at the surface, on the other hand, you go from very warm temperatures, particularly in the tropical and subtropical regions, all the way to mid-latitudes, about 42 degree north and south latitudes. You see all these warm colors with temperatures above 25 degree Celsius. And the temperature changes show typical V-shape profile here. And below 1,000 meters, you see that the temperature change is relatively small, to the tune of only 4 or 5 degrees Celsius as you go deeper. And the isotherms at these deeper depths have a U-shape sort of profile character to them, particularly as you go towards the polar regions. So the purple region in the south, which contains this 0 degree water in purple, beyond the 50 degrees south latitude, that is the Antarctic seawater. And it's very cold. It's permanently cold, and it basically sinks near the Antarctic continent and sinks very deep and goes down and forms this deep, cold water mass. And we're going to talk about that when we get into water circulation and water current systems. And this Antarctic deep sea water, which is extremely cold, basically starts going towards the equatorial region, but then sharply truncated by the mid-ocean ridge system and the seamounts in the Atlantic Ocean. And as you go towards the north, you see that the water temperatures are also basically getting very cold and sort of starts curving up and becoming closer to the surface. Now let's take a look at along the very same walking line, along the same profile. We're going to take a look at this salinity profile of the Atlantic Ocean from about 55 degrees south to 65 degrees north latitudes. So again, this is a vertical profile. You're going down to 6,000 meters. Here are the latitudinal changes. That's the equatorial zone. And This time our color code on the right hand side shows salinity in terms of per thousand. So the salinity is increasing from cold colors to warm colors in this case. And this is the seafloor, again with highly exaggerated bathymetric profile. So again, in the Atlantic Ocean, we see the high salinity seawater between about 38 degrees south to about 45-50 degree north latitudes. And this high salinity water band is an artifact of basically enormously high solar radiation and high rates of evaporation, creating this high salinity in the Atlantic Ocean. In fact, this particular part of the Atlantic Ocean, where we have about between 25 to 42 degree north latitudes, we call that an ocean desert in the north central Atlantic Ocean. And this high salinity basically is one of the most characteristic physical properties of the central Atlantic Ocean in the north that we will talk about later on. And as you go towards the south, you realize that we have low salinity surface water layer right there. And this is basically very cold water coming from the Antarctic, near the circumantarctic ocean water system. And because of its extremely cold temperatures, it is actually sinking and forming this tongue-shaped layer in the Atlantic Ocean. Okay, so we just looked at the Atlantic Ocean in terms of its temperature and salinity profiles. The last thing I want to show you and talk to you about today is seasonal changes of the surface layer temperatures in polar oceans. So I took the example of Weddell Sea in the South Polar region near the Antarctic continent. So we're going to look at seasonal changes in the polar ocean system in the south. And this is called density-driven vertical circulation based on temperature changes and also based on the salt content and the salinity changes of the ocean water. So collectively, we call that thermohaline circulation. Thermo comes from the temperatures and haline comes from the salt contents and therefore the salinity. And so the water density in polar regions strongly controlled by first temperatures and then salinity changes. And as we talked about earlier, the surface water is extremely mixed because of the wind patterns and waves and very choppy surface of the seawater that really mixes the top about 40-50 meters of ocean water and makes it very homogeneous in terms of temperature changes and salinity properties. But after that, things change very rapidly and depending on the seasonal changes. Let's take a look at 4 seasons in the Weddell Sea in the south, near the South Pole. So the summertime, the surface water warms up. Obviously, the solar radiation is high, and in their own summer in the southern hemisphere, the surface water warms and becomes pretty stable. So that's a well-mixed layer within the first 15-20 meters. You see temperatures going up to nearly about 17-18 degrees Celsius. And then you end up with basically going deeper, and the temperatures change very rapidly with depth, and you see this curve with a steep gradient, and we call that thermocline. And it turns out that in the polar regions we have two thermoclines. One is the shallow thermocline with very rapid changes in seawater temperatures close to the surface, and the other one is deep thermocline, deeper into the ocean. So in the summertime, very prominent shallow thermocline, and then by the time you get to about 40, 50 meters below the sea level, the temperatures sort of start getting a little bit stable, but still cooling. And then you get into about 100 meters or so, you see water temperatures again changing, not quite as dramatically as a shallow thermocline, but very steady state cooling taking place. So this is the deep thermocline in the summertime in the southern polar ocean system. Now in the fall, surface water basically cools off very rapidly because of the atmospheric conditions and strong cold winds blowing over the surface of the southern ocean system. So you realize that the temperatures went down by as much as 7 degrees here, and you realize that this water, basically cold surface water, penetrates deeper into the water column now by as much as 40 meters, in contrast to the well mixed zone, which was more shallow. And then we have this a very fast change in temperatures with rapid cooling, and that is the shallow thermocline that we looked at and saw in the earlier profile. But you realize that shallow thermocline exists in a very narrow depth in the fall, and then with depth, basically seawater keeps getting colder with increasing depth in the fall time as well. In the winter time, the polar ocean waters are extremely cold because the surface temperatures are very cold due to the diminished atmospheric temperatures. And so notice that right now we have about 7-8 degrees Celsius surface water, very cold. And that cold surface water actually is continuing all the way down to 80 meters at depth. Very well mixed cold surface water, and our shallow thermocline totally disappeared that we had in both summer and fall profiles. So that's basically a very vertical and same cold water going all the way down to nearly 80 meters. And then after 80 meters or so, with increasing depth, seawater keeps getting colder. So that forms that deep thermocline that we saw earlier, but that is the most prominent thermocline in the winter time right now. And in the springtime, coming out of winter, of course, the solar radiation is much more important early in the spring, and later into the spring, the surface waters start becoming warmer, so you see that the temperatures increased beyond 10 degrees Celsius, and we have a very well mixed layer within the first 25-30 meters of the ocean. And we have that very well defined shallow thermocline indicating rapid changes in temperature with depth. And then water temperatures become pretty stable and cold all the way down towards 80 meters. And then we hit the second deep thermocline, whereby the temperatures again decrease significantly. So these four profiles tell us that basically the temperature profiles of particularly polar ocean waters heavily depending on the seasons. And so, with the changing rates of solar radiation, the water temperatures change very significantly, and also with depth, water profiles, temperature profiles change very rapidly as well. Okay, so that's the end of this lecture on density structure and density profiles of ocean waters. And the next thing we're going to do is that we're going to be talking about air-sea interactions and how the atmospheric circulation patterns affect the ocean water temperatures and ocean circulation patterns, and therefore different water masses and their geographic distribution in the oceans. So, with that, I wish you good luck with your studies and talk to you soon.